Hi guys, welcome back. So today what we're going to be looking at is volumes of a revolution. And this is a little bit different to the previous volumes of revolution that we've looked at, because rather than finding the area, or the volume I should say, of a revolution formed by a function, between a function and the axis, we're actually going to be looking between two functions. And so when we have two functions and we take those functions and we rotate those functions around the x-axis, we create this hollow shape. So it's a bit hard to sort of draw this in a 2D way. But if you were to imagine, this purple is extending and wrapping around here. So we're forming this almost like this hollow shape, like a bead or like a circular washer. So how would I then go ahead and find the volume of this washer, or this strange bead shape that we've made? Well, what we can do is we can actually chop each of these into a disc or a washer, and we can find the area of each of these. So it's going to be pretty straightforward to do this, because these shapes actually form circles. And so if we wanted to find the area of each of these discs or each of these circles, all we would need to do is we would need to find the area of the outer circle, and we would need to subtract that from the area of the inner circle. So in this case here, if we wanted to then add up all of those discs and then ensuring that those discs were infinitely small, so cut up into infinitely small shapes, then we can use integration to do so. So all I've done, the only difference between this formula here and this formula here is, first of all, this sum of all the discs between our region. So in this case, we've got A is just here and we've got B is just here. And I've replaced my radius values with my value for Y. Another alternative to this is we could be using g of x and f of x. So if I go back to my original function now, when I'm choosing which function is going to be subtracted from the other, I'm going to be looking for this function here on top. So I want to draw a quick sketch or to graph in my graphics calculator, so I know which function is going to be on top, so I know which function I'll be subtracting from the other. So that's how we ended up with this equation here. So in this case, my g of x, my red line, was on top. So I'm going to subtract my blue line, f of x, from that function. So then what if we were to rotate around the y-axis? Well, I'm sure you can appreciate this is going to be a pretty similar method, because when we rotate this area or these two functions around, this area is again going to form this 3D washer shape, or this bead shape, where we have this hole that's running through the middle. Okay, so instead of using y's or substituting in values of y for the radius, we can now see that we're going to be able to, this value from here to here is going to be equivalent to our x value of that function. So what we can do is we can substitute in each value for x, and we'll be integrating with respect to y, or we could be integrating the functions themselves with respect to y. Okay, so let's have a go at this question here. So determine the volume form when the area bound by the curve y is equal to 9x squared and the line y is equal to 5 is rotated about the x and y axis. So the first thing I want to do is I want to see which function is going to be on top, because that will tell me what I need to subtract. So I just did a quick sketch of this in Desmos. So I would suggest doing a quick sketch of this using your graphics calculator if you're in a Tech Active exam, or I would suggest doing just a quick sketch if you do encounter this question in a Tech Free exam. And the only reason we do this again is just to see which function is going to be on top, so which function we're subtracting from the other. So in this case here, this area, we can see this red line, this red function, this is our y is equal to 9 minus x squared. And for the region here, this red line is on top. And so therefore, we're going to subtract this blue line, y is equal to 5, from our red line. The other pieces of information that we need to know is we need to know the position of A and B. Now, because I've done this using a graphing program, I can actually calculate this really easily. So if you do have the option to do so, do it with your graphics calculator, just for the sake of brevity. But what we can do if we didn't is we could just treat this as a set of simultaneous equations, and then we could solve to find the values of x that we need. So in this case, we're going to have x squared is equal to 4, and so x could be equal to positive or negative 2. So I can substitute those values in, and I can also substitute those equation 9 minus x squared and y is equal to 5 into my integration function now. So once I've substituted these values in, so you can see I'm going to do 9 minus x squared, take away 5 squared. So I can expand this function out now, and then I can integrate this simplified function. Okay, so what I did then, once I integrated, keeping in mind this pi value here, this is a constant, so I can actually just move him and pop him out the front here. So that's why I've got this pi out the front here. And then I want to substitute in values of -2 and 2. And what we're going to do is we're going to subtract these two functions to find that volume. So once I put those values into my function and subtracted the 2, I found that the total area of this, or the total volume of this region, was going to be 704 pi over 5, or about 442. So then how would we go about rotating around the y-axis? Now this is going to be a little bit different to the previous method, and the reason for that is because when I rotate this function around the y-axis, there's not actually going to be any gaps, so we don't have to treat it like it's a bead or like it's a washer. So we can treat this like we've treated problems in the past. So for this problem, we're going to be looking at integrating the function from a to b, because we're now doing this with respect to y. And we're going to, again, be multiplying this by some value of pi. So I could probably just pop that value of pi out the front. But all I'm going to do is I'm going to integrate that function for f of y squared dy. And in this case, this is going to be this top function. So that was our 9 minus x squared function. So since we have f of x is equal to 9 minus x squared, we're going to rearrange this. So what we could really do, we could write this as y is equal to 9 minus x squared. And we can then go y minus 9 is equal to negative x squared. And so therefore negative y plus 9 to the power of 1/2 is going to be equal to x. So what we can go ahead and do is we can then substitute this function now, because we're looking at a function with respect to y. So in other words, we're looking at this value for x, because they are equivalent. So we can substitute this function in now. And what we need to do is find our values for a and for b. So looking at our graph here, this is going to be pretty easy to work out. We can see, or pretty obviously, that this bottom function, y is equal to 5. So therefore, a is going to be equal to 5 at that point. Now the quadratic, that's going to be a little bit trickier, but the top of this quadratic is going to be at the turning point. So we could use a turning point formula or derivative of the function to find that value for y. So just looking at my graph here, I know that b will be equal to 9. So I've got my values for a and b, and I've got my function with respect to y, so I can go ahead and substitute that now into that equation. So the next thing I want to do is I want to try and simplify this function. Since this is to the power of 1/2, this is the same as saying the square root, so I don't think I'm going to be able to simplify this. So what we can do instead is we can use some of our other integration techniques, so like our reverse chain rule, to help us to solve this particular integral. All right, so now all we need to do is we just need to perform our actual integration steps. So this negative, this can come out the front, so you're ending up with negative pi for u to the power of 3 over 2, and we're going to divide by this new power. So dividing by 3/2 is the same as multiplying by 2/3. Now, I'm a little bit hesitant to write just 5 and 9 here, because when we changed this to integrate with respect to u, we didn't actually change the values 9 and 5 with respect to u. So these are still with respect to y. So there's two ways we could go about this. The first way is that we could substitute in values of y here, and we could find those new values of u. Or alternatively, we can just write this as our function with respect to y again. So we have 2, 9 minus y to the power of 3 over 2 over 3. And then we can just write our normal numbers. And so now let's go ahead and let's substitute these values in to find our solution. So gone ahead and substituted, and I've gotten 16 pi over 3 as my solution. So that would be the volume of this revolution of this solid. And again, because this is with respect to y, just to summarize what we've done, we've gone ahead and we've found the two y values between which we're trying to find this volume. We've also gone ahead and rewritten this function f of x in terms of y instead. And then we've substituted and integrated to solve to find this volume. So again, let's just go ahead and let's summarize what we've done in our previous example. So we found the coordinates between which we're finding, and these are now with respect to x. And then we had to subtract the two functions because this actually does form a hollow shape when it's revolved around the x-axis. So we've gone ahead, we've used our function, we've integrated with respect to that function, and then we've gotten our solution. So that's how we find the volume of revolutions of solids. So using those two methods, so using that bead method or that washer method, and then using the disk method when there was no gap or no space in between. All right, so I hope you enjoyed, and I will see you in the next video. Bye, guys.